What is the main motivation behind the development of the PiSSA method?
The main motivation behind the development of the PiSSA method is to utilize the low intrinsic dimension of pre-trained weight matrices directly, specifically focusing on the principal singular values and vectors of the model. By initializing updatable adapter layers with these principal components, PiSSA aims to preserve the essential capabilities of the pre-trained model while enabling effective and efficient fine-tuning. This approach diverges from methods like LoRA by directly incorporating the principal components of the weight matrices, allowing for faster and better fitting to the training data. PiSSA's goal is to reduce the number of trainable parameters needed for fine-tuning while maintaining or even surpassing the performance of full parameter fine-tuning, ultimately enhancing the adaptability and robustness of large language models across various downstream tasks.
How does LoRA differ from PiSSA in terms of the approach to fine-tuning large language models?
LoRA and PiSSA differ in their approach to fine-tuning large language models, primarily in how they handle weight adjustments during model adaptation. LoRA focuses on approximating weight updates with low-rank properties, substituting updates with a low-rank decomposition delta W equals AB, where A and B are low-rank matrices. In contrast, PiSSA directly utilizes the low intrinsic dimension of pre-trained weights by applying singular value decomposition, SVD, to the weight matrix W. PiSSA divides W into principal and residual matrices, where the principal matrix is fully tunable from the beginning, while the residual matrix is kept frozen. This allows PiSSA to fit the training data faster and better by fine-tuning essential parts of the model immediately. Additionally, PiSSA initializes adapter layers with principal singular values and vectors, preserving the model's primary capabilities while reducing the number of trainable parameters significantly. Overall, while LoRA approximates weight updates with low-rank decompositions, PiSSA directly utilizes the low-rank characteristics of pre-trained weights to enhance fine-tuning efficiency and performance.
Explain the process of singular value decomposition, SVD, in the context of PiSSA.
In the context of PiSSA, the process of singular value decomposition, SVD, involves decomposing the weight matrix W within the self-attention and multi-layer perceptron, MLP layers into three matrices, U, S, and V-T. Here, U and V are singular vectors with orthogonal columns, and S is a diagonal matrix containing singular values arranged in descending order. The SVD operation transforms W into W equals U CDOT, text diag S, CDOT V-T. When the top R singular values are significantly larger than the remaining ones, the intrinsic rank of W is denoted as R. The principal singular values and vectors denoted as U_R, S_R, V_R are used to initialize the injected adapter matrices A and B. On the other hand, the residual singular values and vectors denoted as U_R, S_R, V_R are utilized to construct the residual matrix W_res. By dividing W into principal and residual components, PiSSA ensures that the adapter AB captures the primary capabilities of the pre-trained model, facilitating effective fine-tuning with reduced parameters while maintaining model performance.
What are the components of the principal matrix in PiSSA, and how are they initialized?
The components of the principal matrix in PiSSA are the matrices A and B. These matrices are initialized based on the principal singular values and vectors obtained from the singular value decomposition, SVD, of the pre-trained weight matrix W. The principal matrix W_pre is of low rank and can be represented by the product of A in math BBR_M times R and B in math BBR_R times N, where R lec min M N. The principal singular values and vectors denoted as U_R, S_R, V_R are used to initialize the matrices A and B. These matrices are trainable, allowing for effective fine-tuning of the model while preserving its essential capabilities. The residual matrix W_res, on the other hand, is initialized with the product of the residual singular values and vectors obtained from the SVD and remains frozen during the fine-tuning process.
How does PiSSA ensure that the model's capabilities are not compromised during the fine-tuning process?
PiSSA ensures that the model's capabilities are not compromised during the fine-tuning process by utilizing the principal singular values and vectors of the pre-trained model to initialize the injected adapter. This initialization allows PiSSA to preserve the essential capabilities of the model from the beginning of training. By dividing the singular value decomposition of the weight matrix into principal and residual components, PiSSA focuses on updating the essential part, W-pre, while keeping the less important part, W-res, frozen. This approach enables PiSSA to fit the training data faster and better, as the essential components are fully tunable from the start. Unlike LoRA, where a significant part of the weight matrix is kept frozen initially, PiSSA's strategy of updating the principal components ensures that the model's capabilities are maintained throughout the fine-tuning process. Additionally, by reducing the number of trainable parameters and utilizing a linear structure for the adapter, PiSSA can effectively fine-tune the model with reduced memory consumption and without compromising its original capabilities.
What are the advantages of using principal singular values and vectors for initializing adapters in PiSSA compared to other methods?
The advantages of using principal singular values and vectors for initializing adapters in PiSSA compared to other methods lie in the superior fine-tuning performance and efficiency it offers. By directly fine-tuning the model's principal components based on the principal singular values and vectors, PiSSA demonstrates enhanced outcomes on downstream tasks, leading to reduced training loss and improved accuracy. This approach allows PiSSA to converge more swiftly, align closely with the training data, and achieve a level of fitting to the training set similar to full parameter fine-tuning with fewer trainable parameters. Additionally, PiSSA outperforms other methods like LoRA by consistently maintaining lower loss levels throughout the training process and surpassing the performance of full parameter fine-tuning as the rank increases. The utilization of principal singular values and vectors in PiSSA enables faster and better fitting to the training data, resulting in improved generalization performance and robustness on downstream tasks.
Describe the experimental setup mentioned in the paper for conducting comparative experiments between PiSSA, LoRA, and full parameter fine-tuning.
The experimental setup for conducting comparative experiments between PiSSA, LoRA, and full parameter fine-tuning involved fine-tuning Llama 2-7B, Mistral 7BV0. 1 and Gemma 7B on tasks such as math, coding, and instruction tuning. The experiments utilized the Alpaca implementation strategy, employed the Atom W optimizer with a batch size of 128, a learning rate of 2E5, cosine annealing schedules, and a warm-up ratio of 0.03, without any weight decay. The computation type used was BF16. The experiments incorporated adapters into all linear layers of the base model and trained only on the first 100,000 conversions from the dataset for one epoch, using the response of the conversions to compute loss. The experiments were conducted on the NVIDIA A800SXM 480G GPU. The results of the experiments demonstrated that fine-tuning adapters initialized with principal singular values and vectors, PiSSA, outperformed those initialized with intermediate or less significant ones, showcasing the effectiveness of directly fine-tuning the model's principal components for superior outcomes.
What are the key findings from the experiments conducted on Llama 2-7B, Mistral 7BV 0.1, and Gemma 7B using PiSSA, LoRA, and full parameter fine-tuning?
The key findings from the experiments conducted on Llama 2-7B, Mistral 7BV0. 1 and Gemma 7B using PiSSA, LoRA, and full parameter fine-tuning are as follows. 1. PiSSA outperforms LoRA and full parameter fine-tuning across various tasks, including math, coding, and instruction tuning. 2. PiSSA demonstrates superior performance by initializing adapters with principal singular values and vectors, leading to reduced training loss and enhanced accuracy on validation datasets. 3. PiSSA converges more swiftly and aligns more closely with the training data compared to LoRA, exhibiting robust superiority under the same trainable parameter configurations. 4. PiSSA achieves a level of fitting to the training set similar to full parameter fine-tuning with fewer trainable parameters, showcasing improved robustness and generalization on downstream tasks. 5. As the rank increases, PiSSA quickly surpasses the performance of full parameter fine-tuning, indicating the effectiveness of utilizing principal singular values and vectors for fine-tuning. 6. Fine-tuning with PiSSA consistently leads to lower training loss and enhanced accuracy on validation datasets compared to LoRA, showcasing the efficacy of fine-tuning based on principal singular values. 7. PiSSA's approach of replacing full parameter model fine-tuning with principal components results in models with improved robustness and superior performance across tasks. 8. The experiments highlight that PiSSA's strategy of fine-tuning model parameters based on principal singular values leads to superior outcomes compared to other methods. 9. PiSSA's ability to converge quickly, maintain low training loss, and outperform LoRA and full parameter fine-tuning across tasks underscores its effectiveness in enhancing model performance. 10. Overall, the experiments demonstrate that PiSSA is a highly effective fine-tuning method that offers improved performance, faster convergence, and enhanced robustness compared to LoRA and full parameter fine-tuning approaches.
How does the rank of PiSSA affect its convergence and performance compared to LoRA?
The rank of PiSSA affects its convergence and performance compared to LoRA by influencing the speed at which the model converges and the effectiveness of the fine-tuning process. In the experiments conducted, it was observed that at the beginning of training, PiSSA quickly starts to converge, while LoRA experiences a period where the loss may not decrease and could even slightly increase. Throughout the training process, PiSSA consistently maintains a lower level of loss compared to LoRA. As the rank of PiSSA increases, it converges more swiftly and aligns more closely with the training data, outperforming LoRA under the same trainable parameter configurations. Additionally, PiSSA achieves a level of fitting to the training set similar to full parameter fine-tuning with fewer trainable parameters. As the rank of PiSSA increases, it quickly surpasses the performance of full parameter fine-tuning, indicating that focusing on the principal singular values and vectors leads to improved robustness and superior performance in downstream tasks.
What is the significance of the fast SVD technique mentioned in the paper, and how does it contribute to the initialization process in PiSSA?
The fast SVD technique mentioned in the paper is significant as it helps speed up the decomposition of the pre-trained matrix W in the PiSSA initialization process. The fast SVD algorithm, proposed by Halko et al., introduces randomness to achieve an approximate matrix decomposition, which results in a faster computation time compared to traditional SVD. This technique is crucial for the initialization process in PiSSA because it reduces the time required for singular value decomposition, making the method more efficient and practical for real-world applications. Additionally, fast SVD helps in achieving a balance between initialization speed and performance by providing a quicker alternative to traditional SVD while maintaining a reasonable level of accuracy in the decomposition process. The results presented in the paper show that fast SVD significantly reduces computation time, especially as the rank of the decomposition increases, making it a valuable tool for accelerating the initialization of PiSSA adapters. Furthermore, fast SVD allows for controlling the initialization error by adjusting the number of subspace iterations, NITER, enabling researchers to fine-tune the trade-off between speed and accuracy in the initialization process of PiSSA.